Good morning, everyone. Myself, Yash Vyas. I am a student of IIPS DABV, currently studying in 4th SEM MTech IT. Today, I am going to show the solution of Assignment 1 of Numerical Analysis and Design, assigned by Professor Dr. Saligram Prajapat Sir. In the first question, it is asking the algorithm for finding roots of polynomial equation. Firstly, we are going to write the algorithm of bisection method. We are taking three assumptions. First, the f of x is continuous on the interval a to b, and f of a into f of b is less than 0. And the third one is the tolerance e is greater than 0, but for example, the tolerance can be 0.0001, and the maximum number of iteration is n. Now the algorithm starts with, firstly we take the input, the function f of x, interval a comma b, tolerance e, and the number of maximum iteration n. Then we compute f of x, b of f of b. Then we check if f of a into f of b is greater than 0 or not. If less than 0, then print. If greater than 0, then print invalid and stop. Else repeat for I is equals to 1 to n, and compute the value of m is equals to a plus b by 2. Then compute the f of m. If f of m modulus is less than e, or b minus a divided by 2 is less than e, print m is the root and stop. Or else check if f of a into f of m is less than 0. Then set b is equals to m, else set a is equals to m, and end the root. After that, print the value of m as the approximate root and stop the algo. Then the same logic of the algo is explained in the flowchart given here, where every condition statement is properly mentioned, and the flowchart of this, where and then the time complexity for the following algo slash flowchart is log base 2 big O of log base 2 b minus a divided by tolerance. The space complexity here is big O of 1. The graph here below show the number of four iteration, and how the value changes, how the value of midpoint changes through the four iterations. Now the second method is regular Falsi method. We are taking three assumptions. F of x is continuous in interval a comma b. The f of a into f of b is less than 0. The tolerance is greater than 0, and the n is the number of maximum iteration. The algorithm starts with, we first read the f of x, the interval a comma b, tolerance c, maximum number of iteration, compute the value of a comma b, and then we check whether the f of a into f of b is greater than 0 or not. If it is greater than 0, then we print the invalid interval. The root does not exist in that interval, that means, and stop the condition. Or else we will run a while for loop or loop from I is equals to 1 to n, in which we will first compute the value of x. When you can also see the value of m in the flowchart formula given above the flowchart, and the formula is f of a f of b minus b f of a divided by f of b minus f of a. After computing that, compute the value of f of m. After that, check that the f of m modulus is less than e. If it is less than e, then print the x is the root, x as a root, and stop the loop and the algo. Else check if f of a into f of x is less than 0. If less than 0, then set b is equals to x, else set a is equals to x, and repetition, and then print x as the approximate root and stop the loop. And after stopping the loop, the algo. Then the same algo is explained in this flowchart through the diametrically and in a proper way. You can read it properly after that. Then the time complexity for the given algo slash flowchart is big O of k, and the space complexity is big O of 1. The graph here represents the four iteration of the following, where that how the value of m is changed through the 4 iteration. You can see there is not much change in this, and from the first iteration it is finding the almost approximate value. Now the third method, the secant method. The assumption here are f of x is continuous near the root. The initial guess x0 and x1 are given when the f of x0 is not equals to f of x1. The tolerance is E and the maximum number of iterations are given n. The algo start with we first read the f of x, initial guess x0, x1, tolerance E, the maximum number of iterations. Then we repeat from I is equals to 0 to n. Here we compute f of x, f of 0, 1. And then if the f of x minus f of 0 is equal to 0, print division by 0 and stop the loop. Else f of x is equals to x1 minus f of x1 into x1 minus x0 divide by f of x1 minus f x0, and then check the value of x2 minus x1 modulus is less than equal to 0, or the f of x2 modulus is less than E. Then if any of the conditions is true, then print f of x is equal as root and stop, or else set the x is equals to x0 and x1 is equals to x2 and repeat until the condition I is equals to n, or it stop in between. Then print the x2 as the approximate root and stop the algo. Then now the same thing here is explained in this algo flowchart using the diagrammatically and explaining each condition in the rectangle in the diamond box and the computation in the square box. Now for the time complexity, for the following algo is big O of k and the space complexity is big O of 1. And the graph here show how in the secant method the value of m varies in 4 iterations. Now the fourth method is Newton's method. In this the assumption are f of x and f of f dash x are continuous near the root. The initial guess g f x0 is given. The f dash x is not equal to 0 near the root. The tolerance E is greater than 0 and the maximum number of iterations are n. Algorithm. It starts with the we read the value of f of x, the derivation of f of x, the initial guess and tolerance E, and the maximum number of iteration n. Then we repeat from I is equals to 0 to n. Then we compute the value of f of x comma f dash x, and if f dash x is f dash x is equal to 0, then we print the 0 division, or else we compute the value of x next, which is x minus f of x divided by f dash x. If x next minus x is less than modulus is less than 0, or the f of x next modulus is less than E, then we print x next is as the root and stop. Else we set x is equals to x next and repeat until the condition I is equals to n, and print the approximate value of x as x and stop. Now this flowchart explains this complete algorithm in a proper and beautiful way. Now the time complexity for the Newton's method is big O of n, and the space complexity for this method is big O of 1. And the here graph represent how the tangent and all are represented in the Newton method for 4 iterations. And here we can see the first iteration it is red and second is red. And for the next two iteration, for the next value we are using the green dots to represent that. Now the fifth method is fixed point iteration method. Here the assumption are g of x is continuous in the interval. G dash modulus is less than 1 near the root convergence. Initial guess x0 is given, the tolerance E is greater than 0, and the maximum iteration are given. Starting of the algo start with the taking function g of x, initial guess x0, tolerance c, and maximum number of iteration. Repeat from I is equals to n. Then next x next is equal to g of x. If x next minus x is less than e, print x next as root and stop. Else x set x is equals to x net. Repeat until the x I is equals to 1 n, and then print the x is the approximate root and stop the algo. Now same the algo is explained through the diametrically in this flowchart where the conditions and all are present properly. The stopping condition in this is that x next minus x is greater than 0. E is less than e. Now the time complexity for the following algorithm is big O of k, and the space complexity for the following algo is 1, big O of 1. Now this diagram shows the geometrical interpretation of this method, where how the uh, value of m r value of x is varying from first iteration to the fourth iteration. Now the question number 2 asks us to write the algo for applying interpolation using first method is Lagrange's interpolation, where the assumption are x points are distinct and y points are known at each x point value. Firstly, we read the x point and y point and the value of x, then set the result is equal to 0. Then we repeat from I is equals to 0 to I is equal to n minus 1 and set the term is equals to y point bracket y, so that the array. Then we repeat from j is equals to 0 to j is equal to 1. If the j is not equal to I, then term is equals to term into x minus x point j divide by x point I minus x point j. Then end the loop for the j. Then result is equal to result plus term. Then end the loop for the I, and then print the result. Print the result is equals to print the result and then stop the algo. Now this Lagrange's algorithm is explained in this flowchart properly. You can go through it where every condition is represented in the a diamond shaped box, and the computation and reading is written in the square box. The time complexity for the following algorithm is n square, and the space complexity is big O of n. Here the graphs show the different points of the Lagrange's interpolation and the final value of our data which we have find. The next method is Hamilton interpolation. Here the assumptions are x point are distinct, y point and dy points are known at each x point value. The algorithm starts with read x point, y point, dy point and x. Build x and q table with repeat nodes. Fill first column of q with y value. Fill the first divide with difference using dy points and finite difference. Compute the higher order differential divided difference. Evaluate the interpolation polynomial at x. Then print the value which is our answer of the interpolation, and then end the loop and end the algo. The interpolation The Hamilton interpolation flowchart represent the following algo properly, which we can understand. The time complexity for the following algo is big O of n square, and the space complexity for the following algo is big O of n. The graph represent the data points and the result, how we find it, and all the data point properly. The next third method is divide and difference table. In this, we are assuming x points are distinct, y points are known at each x point value. The algo starts with we read the value of x point and y point, set first column of table to y points for each order j is equals to 1, 2 and minus 1, compute the divide and difference using the formula, and then we print the table, and here's the algo. Now in the flowchart we can see we have initially read the algo, then uh, compute the values of the table using the formula I is equals to k plus 1 and di comma 2 is equals to di plus di 1 minus di 1 minus comma 1 divided by xi minus 1 and k plus iteration k plus 2, same goes for di comma 3 is equals to di comma 2 minus di minus 1 by 2 divided by xi minus 2, and the final equation of dij is equals to dij minus di comma j minus 1 divide minus di minus j minus 1 divided by xi comma xi minus j plus 1, and finally we print the table using the loops. The time complexity for the following table creation is big O of n square, and the space complexity is big O of n square. And here the graphs show the values of different data points and their respective x and y values. The difference table. The assumption here are we are taking x value are equally spaced and y values are known for the value of x. Firstly we read the value of y, then set the value first column of table to y values. For each order j is equals to 1 to n, we compute the forward difference using the forward difference formula, and then after that we compute the forward difference formula, where we minus the next value from the previous value, and after that we print the table and the algo stop. Then here in the flowchart it is properly explained how the forward difference algo works diagrammatically, and how we have to initialize the values. The algorithm time complexity for the following algorithm is big O of n square, and the space complexity for the algorithm is n square. The graphs shown below show how the values are in the interpolation different forward difference table are placed for x and y, where all the value of x are equidistanced and y may vary. The fifth method is Newton interpolation using difference. The assumption here are x points are equal spaced and y points are known for each value. X is within the interpolation range. The algo starts with read the x points comma y values and the x, compute h is equals to x point 1 minus x point 0. Then build the forward difference table. Then compute the value of p, which is equal to x minus x point 0 divided by h. Then evaluate the polynomial using the p and the forward difference table, and after computing the value, print the value as the answer of the interpolation, and then stop the algo. Here every step in the of the algo is present properly in the flowchart, where we have properly indicate how the table is created and how it is printed, and then how the values are computed in this and all the loops. Now the time complexity and the space complexity for the Newton forward interpolation is n square, same in both. The graphs show the different data points and the finded data points, and where each x value of x is equidistant and value of y distance may vary. Now the third question is algorithm for the numerical difference using first method. Method based on interpolation. The assumption here are x points are distinct, y points are known at each point x value. X is written within the interpolation range. The algo starts with we the x point and y point and x. For each I, compute the derivation of Lagrange's basic at x, sum y point I into the basic derivation divide to give the derivative. Then in the end we print the derivative and stop the algo. Then in the flowchart it is given how the loops are working from I is equals to n, and then we check the condition, and the in the loop for j is equals to 0 to k for the data points, and then we compute the value of x difference divided difference, and after that we computing an ending of the loop, we print the table and the answer of the new interpolation method. The algorithm flow time complexity is big O of n cube and space complexity is big O of 1. The graph here represent the geometrical interpretation of the following algo, where the blue line represents the interpolating polynomial, the dotted line is the tangent as the x point. X point is the point at which we are evaluating the answer, and the red points are the data points. The second method is difference based on finite difference. The assumption here of f of x is differentiable near x. The step size h is greater than 0, but is a small value like 0.001, and the algorithm start with function f of x. We read the f of x, the point x, and the size h. Then we compute the forward difference f of x plus h minus f of x divided by h. We compute the backward difference using the f of x minus h divided by h, and the central difference using f of x plus h minus f of x minus h divided by 2h. Then we print the approximate value for the following and then stop. And here the flowchart represent the algo properly. And the space complexity and time complexity for the algorithm is big O of 1, same for both. Then the geometrical representation of this method, so the polynomial f of x using blue line, the tangent using the dotted line, and the x is the point where we are the value which we are trying to get. The fourth method is accuracy evaluation of the Newton's versus Lagrange's interpolation method. In this, the time complexity is big O of n and the space complexity is big O of 1. The graph here shows the geometrical interpretation of the following method. The second method is Gaussian quadrature formula 2 points. In this, the f of x is continuous on a comma b, and the 2-point Gaussian rule is used. Start we read the function f of x, limit a comma b, set t1 is equals to minus 1 divided by square root of 3, and set t2 is equals to 1 divided by square root of 3. Then we map the nodes to a comma b to get the value of x comma 2. The approximate integral is equals to b minus a divided by 2 into f of x1 plus f of x2. Then we print the result, and here's the how the algorithm ends. Then same algorithm is presented using the flowchart for 2-point Gaussian formula. The time complexity for the 2-point Gaussian formula or all the Gaussian formula is big O of n, and the space complexity is also big O of n. Now here the geometrical interpretation, the graph show the f of x using the blue line, and the Gaussian nodes are represented using the red dots. Now fifth question, solve the linear equation using first method, which is direct method for solving the system of linear equations. The first method for the 5.5 is Gaussian elimination method. Here we are taking assumption as A is a square matrix and B has a matched size. A is non-singular. The algorithm starts. Read the value of matrix A and vector B for augmented matrix A, B. For loop for k is equals to 0 to n minus 1, choose the pivot row and swipe. Then for I is equals to k plus 1 to n, another loop starts. Eliminating the entire entities below the pivot. After that, end the for loop for I and then end the for loop for k. Then backward substitution to solve for the value of x, and after finding that, print the value of x and stop the loop. And the time complexity for the given algo is n cube and space complexity is n square. Now in the Gaussian elimination method, the flowchart represents how the forward elimination is working properly. Here the loop starts from n and then check whether the n is less than k is less than n minus 1. If k is less than n minus 1, then I is equals to k plus 1, then n is equals to a of I comma k divided by k comma k. Then it's checked whether the j plus k plus 1, which is 3c, compute the 3c, and after that, if the false, then it check whether the j is less than n plus 1 or not. If it's true, then a of I comma j is equal to a of I comma j minus m into a of k comma j. And if it's wrong, then it's again check the continue condition until the uh, j of less than n plus 1 is true. After that, the backward substitution starts. In the backward substitution, n is equals x of n is greater than n of comma n plus 1 divided by a of n, and I is greater than or equal to 1, then the sum is equals to 0, then j of I is equals to 1, then we compute the value of sum. After that, we check whether the j of uh, j is less than n. If it is less than n, then we compute for the value of I, and then after that, ending of the loop when the value of j is less than n, greater than n, then we get the answer, and then we print the value of x2, which is our answer. Now the next method is the Jacobi's algorithm for iteration method. The Jacobi iteration method, the assumption are A is square and diagonal dominant for convergence. Initial guesses x0 is given or 0. Tolerance is E. The maximum iteration n are given. The algorithm for Jacobi iteration start with reading A, B, x0 tolerance E, maximum iteration n. For I is equals to 1 to n, compute the new value x using the pivot iteration value. Compute the error is equals to maximum of n minus nu minus x modulus. If the error is less than e, then print x and stop, or else set x is equals to x nu and end for. Print x as a approximate solution and stop. Now the complete algo is shown in this flowchart. Now the time complexity for the following is k into n square, and the space complexity is n square. Now the graph here shows how the error n versus iteration in the Jacobi's, how the error drastically reduces in the starting few steps of the Jacobi method, and after that it changes less significantly. Now the third and last method is Gaussian slider method. Here the assumption are A is a square and diagonally dominant or convergent. Initial guess x0 is given or 0. Tolerance is E is greater than 0, and the maximum number of iteration n. Start. Read A, B, x0 tolerance E, maximum number of iteration n. For I is equals to 1 to n. Update x in place using the latest value. Compute the error x is equal to maximum of x minus x hold. If the error is less than 0, print the value of x and stop the for loop. And after that, print the value of x as the approximate solution and end the algorithm. Now same algorithm, we have given a formula which we can show in the flowchart properly, which I can't speak. It's very complicated to speak. So you can see that, and also the condition for stopping is also here in the algorithm, the last condition which you can see. The time complexity for the following algorithm is k into n square, and the space complexity is n square. The graph show the error versus iteration in the Gaussian slider. Here it is taking three iteration, and after that the changes in the error is very less significant. That means after three to four iteration, in less iteration, the answer is coming. Now fourth, approximation method. The first method is least square approximation. The assumption here are x value are distinct and paired with x value. The linear relationship is a reasonable model. The algorithm start with we read x value and y value, compute the sum xs, xy, xx and xxy. Then we compute the denominator, that is equal to n into x xx minus x x square. After computing that, we compute the slope b and the intercept a. After that, we print the value of a and b, and here's the algorithm end. Now here all the conditions are in the computation equation are properly mentioned in the flowchart, which you can see. The time complexity for the following is big O of n, and the space complexity is big O of 1. Now here the graph show the best fit line for the data for least square interlinear fit. Now the next method is polynomial approximation using orthogonal polynomial. The assumption here are f of x in integer and on interval -1 to 1. Degree b is chosen from approximation. The algo start with we read the function f of x in degree d for n is equals to d loops, compute the coefficient using the inner product using Lagrange polynomial, and then end the loop, then evaluate the approximate value of at x, and then print the value. After that, stop. Here the equations are properly mentioned, which you can see in the flowcharts. The time complexity is d into m square, and the space complexity is big O of d. The geometrical interpretation of the orthogonal polynomial approximation, the orange line represent the Lagrange approximation, and the blue line represent the f of x, which is almost coinciding each other. The last question, the algorithm for ordinal differential equation. The first is Lagrange method, Euler's method. Assumption are f of x is continuous in interval. Initial condition x0 y of x0 is equal to y0 is given. The step size h is greater than 0. The number of steps n is given. The start, read the f of x comma y, read x0 y0 h n. Set x0 x is equal to x0 and y is equal to y0. Repeat for I is equal to 1 to n. Y is equals to y plus h into f of x into y, x comma y. Then x is equals to x plus h, and repeat until the I is equals to n. After that, print the value of y and stop the algo. Now you can see properly all the methods in the flowcharts for the Euler method. The time complexity and the space complexity for the Euler method is big O of n, and the geometrical interpretation, you can see how the values changes in the Euler method. The last method is Runge-Kutta method or single step method. The assumptions are f of x comma y is continuous in interval. Initial condition y is x0 is equals to y0 is given. The step size is greater than 0, and the number of steps is n given. The algorithm starts with read the f of x comma y, read x0 y0 h n, set x0 x is equal to x0 y is equal to y0, repeat the loop for I is equals to 1 to n, and compute the value of k is equal to f of x comma y, k2 is equals to f of x plus h by 2 comma y plus h into k1 by 2, x3 is equals to f of x plus h2 by comma y plus h into k divided by 2 by and f of and k is equals to f of x plus h comma y plus h into k3, and then the value of y is equals to h divided by 6 into k1 plus k2 into 2 plus 2 into k3 plus k4, and the new value of h x is equals to x plus h, and then end the loop. After that, print the value. After the end of loop, print the value of y, which is our answer. Now all the equations are properly represented in this flowchart. The time complexity and the space complexity for the Runge-Kutta method of fourth order is big O of n, and the geometrical interpretation show how the values are changing in the respect of x, y. Thank you for this wonderful session with me.